Okay, so let us start with these instructions. Ashwin, this is activity number 3, right? We have already done 2 activities. One was on classical mechanics. Second was something related to quantum mechanics. I think harmonic oscillator. And the third one is this one that we are going to do today. Chalk चाहिए और ये जरा साफ कर दो. Third one we are going to do in waves and oscillations. And instructions और चालू किया. हाँ, but you can say, take this chair. So we will do this in oscillations, this activity. And next activity we will have it after uh, CIA, and that would be um, related to what Rohan sir is currently teaching, electricity and magnetism and Laplace equation and charged particles. So Laplace equation sir का favorite है, 1D, 2D, 3D. So he may give you some activity in that. Okay. So today we are going to look at the science of damped oscillator. Just check if the feed is coming or not. उसको जरा link group में share कर दो. Although I had created, for a change, I had created today's scheduled today's link very early in the morning, but we could not have it. So okay. So what is damped harmonic oscillator? So remember here, technicalities are largely the same. We already know how to solve the differential equations. So that part is something which is not new. So I would largely leave that part for you people to handle, because way we have solved uh, equations so far, using Euler's method, we are going to use the same. Me? Yes. 1 minute. Hello? No, I don't think it is connected. Yeah, I should be audible now. Okay. So if I'm not audible, then let me know on the live feed. So damped harmonic oscillator is something that we are now looking into. So as I said, the methods of solution are the same that you have exploited earlier. So I would rather leave that part for you people to figure it out. I would rather focus on the science. Uh, why this topic? Because I feel that in the lower class, particularly in the course of 1.01, this is just touched upon, not done in detail. And I don't think it is revisited in 5.01. So it is something which is important in our day-to-day life, because in day-to-day life, all the oscillations are going to be damped oscillations. And therefore, we need to understand it. So just you can note down the science part. We are familiar with this equation, and we will look at a force which is proportional to the displacement, that is your normal oscillatory force, and we will also see a force which is proportional to first power of velocity. Okay, so this gives us the equation for the damped harmonic oscillator. Okay, so now you can have your regular assessments. So you know that this is d2x by dt square with mass is minus kx minus b v, and d2x by dt square plus, you bring this on this side and divide by m, so b by m into dx by dt plus k by m into x is equal to 0. So this becomes our standard fare. This becomes our standard equation. It is customary to write it in a more compact form. Omega 0 is root k by m. Okay. I don't know if it's visible or not. All I can do is I can zoom in. So it is customary to write it in more compact form. So omega 0 is k by m, which is the natural frequency. Remember, I'm using the word natural frequency of undamped oscillator. So if the same oscillator has been completely undamped, okay, so this would have been the natural frequency. K is force constant, m is mass. Also, we can write gamma is as b by 2m. So what happens typically is b is referred as b is referred as coefficient or damping coefficient. There are different terms. K is force constant. for a given damping coefficient, gamma becomes constant. So normally we can call it as force, sorry, damping constant. Okay. So dimensions you can figure out. This has dimensions of force. So this must have the dimensions of force. This also must have the dimensions of force. Now you know the dimensions of x and v. So you can evaluate the dimensions of k and b, and therefore you can evaluate the dimensions of omega 0 and gamma. I will show you in a while that omega 0 and gamma generally have the same dimensions. Now, how do you solve? So, this equation gets more compact. d2x by dt square plus, now this becomes 2 gamma dx by dt plus, this becomes omega 0 square root sign into x. So, this becomes your final equation, which is generally the defined or definition equation for uh, damped harmonic oscillator. Okay, how do you solve it analytically? I'm not solving it, I'm just talking about it. So one of the easiest way to solve it analytically is that you assume that your solution is oscillatory. Remember that you start with a force which gives you an oscillatory solution. So you assume that your solution is going to be oscillatory. So I assume that my solution is x is equal to a sine or a cos omega t plus some phi. Then you take the first derivative, put it here, take the second derivative, put it here. Then you equate the coefficients. And then eventually you find out two unknowns or three unknowns, a, omega, and phi, in terms of known situations or known constants. So that's a long drawn thing. I'm not going through it. What I am going through it is that my final solution turns out to be some a0 e power minus b by 2m, which is gamma, cos omega t plus phi. Phi remains a constant. So this is our solution. Phi value will eventually depends upon your initial condition. So for example, if you are starting from an extreme end, then your phi value would be 90. Starting from the middle, phi value will be different. So unless those conditions are given, we cannot judge phi. We eventually realize that the amplitude of the resultant oscillation are time dependent. They are not constant. And that is the interesting part. So what you get here is a0 e power minus gamma t. You also see that this omega is different. Omega is b by, sorry, k by m minus b by 2m the whole square. which is nothing but root of omega 0 square minus gamma square, where gamma is defined here. So you can see from this that the gamma and omega 0 must have the same dimensions. Otherwise, this equation will go dimensionally incorrect. So you need to figure out now we must look at the behavior of the system for different B. So you would find that there's a critical case exists when omega can become 0, right? The frequency, I would call this term as again natural frequency of damped oscillator. Natural frequency of the damped oscillator. I'm again using the word natural. It's important. This is unfair. Should be prepared for class, no? Okay. Natural means, whenever we say natural means, if you leave the system on its own, you disturb the system. And once the disturbing source is removed, system is allowed to oscillate on its own. Then whatever frequency the system exhibits is going to be the natural frequency. Okay, so very simply, I take this bench, I tap on it, you heard the sound. Now, if the sound is being produced, that means the oscillations were generated. But then you saw that the sound did not continue for long. That means the oscillations died quickly. Correct? So this is one of the examples. And then there could be plenty of such examples. For example, if you take this rod which is hanging, a plug, displace it by delta x and leave it, you find it will have some oscillation and then finally come to rest. Okay, if you are trying it, be very gentle. Now there are interesting cases over here. You will find that the natural frequency of the damped oscillator is not just decided by K by M, undamped oscillator frequency, but also by B. 2M is a constant, assuming that. So the resistive force will also decide how fast or how slow or how it will oscillate. And you can easily see that a critical case exists when these two terms match. When these two terms match, in that case, K by M is equal to B square upon 4M square. And in this case, the natural frequency is 0. If it is 0, what does it mean? What does it mean if the natural frequency is 0? If the frequency is 0, that means time period is infinite, right? What it physically means is that the system will not come to rest. System will not oscillate, sorry. System will not show an oscillatory behavior, okay? This is a case what we call as critical damping. And this happens for B is equal to root of 4km. So if B is equal to root of 4km, we are in a situation of critical damping. So in a normal case, suppose if you take a simple pendulum, your staple diet, and you swing it in air, you know that it oscillates for a long time, correct? What do you think about B value in this case? I want this. What do you think about the simple pendulum suspended in air that you are handling from your 11th class? You can see that the behavior is, air is present, so resistance is indeed present, but it oscillates for a long time. Okay, so obviously in this case, B value is much less than 4 km. Okay, and this is the case of underdamped oscillator. Okay, if you want to increase the damping, we had tried this once in the lab. What you can do, you can take some water in a dish and allow the simple pendulum's bob to move through the water. Okay, you will find that normally if it takes say 50 oscillation or 100 oscillation to come to rest, there it will take around say 8 or 10 oscillation and come to rest. So what you are doing is you are increasing your B value as compared to this, but oscillations are still happening. That means you are still under damped. Okay, you are still in the under damped scenario. If B is equal to that, you are critically damped. If B is greater than root 4 km, what will be the natural frequency in that case? If B is greater than root 4 km, you will find that the natural frequency of the damped oscillator will become imaginary, right? This term would be larger than this one. And therefore, you will get a situation where the system will, at least in practice, take a very long time, very long time to come back to equilibrium. Obviously, no oscillations at all. Okay. So, if I plot a graph of x versus t, okay, then in the three cases, what kind of behavior I expect? So, if I have a simple pendulum, depends on, suppose I take it to the extreme and then leave, then oscillations start from here. In that case, the phi value would be 90, pi by 2. So in case of a pendulum, you will find that the drop is very slow. It will keep dropping, keep dropping. Why? Because your B is much less, therefore your gamma is much less, therefore this term is reducing very slowly. आ जाओ, आप भी आ जाओ. Okay, so the amplitude drops very slowly, takes a very long amount of time. Okay, so most of the ideal cases that we do in the lab, Cater's pendulum, simple pendulum, bar pendulum, etc., they all fall basically in this category, where damping is present by a small amount, but we are ignoring it altogether, and we are allowing the system to take as much. We are assuming that it continues for a long time. What happens if it is put in water? Then the damping could be much faster, and it will still, there will be some oscillatory behavior. I can change the color, and you will find that the oscillations die out very quickly. So this is, both are under damped. What I showed with this and what I showed with this, both are under damped. But visibly, they are different. One is so much under damped that you will lose patience to see that it's normal, simple, nicely designed simple pendulum hanging from a very rigid support. आप वेट करोगे कि ये कब, अगर आपको पूरा मोशन देखना है तो आपको बहुत देर तक वेट करना पड़ेगा. 100 oscillations, रोहन सर, हम आसानी से लेते हैं ना, राइट? Pendulum will not, it will not be seen much damped. Still damping is there. You might have to go 1,000 or 2,000 oscillations before it fully come to rest. So that is this case. This is still under damped. Put it in water and it will come to rest quickly. Okay. Or maybe if you have any, for example, this, when I'm hitting, a sound is being generated. That means there are oscillations, but they are dying quickly. Okay. Hmm. Yes, yes. That is what the frequency is shifting. No? I talked about frequency omega 2 pi f. So time period will change obviously. So you mean to say this diagram? Diagram I'm just drawing. I'm just focusing on amplitude as of now, not on wavelength. Okay. Yes, that is right. Frequency is, as this factor increases. What sir is saying is, as this factor increases, your omega, that is frequency, is decreasing. So your wavelength lambda. So diagram the should have been slightly longer if it's the same system. If it is critically damped, then there is no oscillatory sorry, there is no oscillatory behavior and it comes to rest. Okay, and some finite time, understandably. And while if it is heavily over damped, last case, then it may take a lot of time before it comes to rest. So this is over damped and this is critically damped. Okay, so that's the entire thing that we want to explore through this activity. So now, for system is concerned, I had something in mind. But before I come to that, you reduce it to first into a velocity equation. So d2x by dt square is actually d2x by dt square is actually dv by dx into dx by dt plus 2 gamma dx by dt plus omega 0 square x is 0, or dv by dx into v plus 2 gamma into v plus omega square x is 0. So you reduce the equation into a function of v on x, solve it, then you solve for the time part. So you reduce it into a two-step solution. I think we did the same thing with uh, particle falling terminal velocity question, right? We have done the same thing. So do that. Your expected graphs are these. You should be able to get 3 graphs. Keep the scale same. Keep the scale same so that a fair comparison is possible between the over damping, under damping, and critically damped cases. All the 3 cases. Okay. So this is the entire task. I would wish to add, but I fear then it will be a lot of work from me. But if you people are enthusiastic, then you can do a few things on your own. So for example, you can take a scale, normal foot ruler, you know, clamp it somewhere with the hand, or and the other end you can hit. So it will vibrate and come to rest. Very simple system. That's a scene where you can figure out how it is oscillating. Typically, it will be under damped, and you can examine that behavior either using video analysis or whatever, and compare it with this. Or if some of you wants to do it later as a project, that also you can do. You can, important thing, I was all the way I was talking about the natural frequency. Why was I talking about the natural frequency? Because the system is left to itself to oscillate. Okay. We can also talk about forced oscillators. That you can think when you are doing projects, right? So in a forced oscillator, you will have these three terms and one more term as the oscillatory force, something like this, F0, some cos omega t. Some oscillatory force will come in the picture, omega prime, where omega prime is the frequency of the forced oscillator. Technically, if it's a forced oscillator, then the system oscillates with the frequency of the driving force and not with its natural frequency. You understand this? So that is where it becomes, this distinction becomes very important, that what we derive, what we are talking about all throughout is natural frequency. And what in a forced oscillator, you system oscillate with the force frequency. And when the force frequency matches with natural frequency, then what do we get? We get the situation of resonance. So that's an interesting project work by which you can solve it for the forced oscillator, then vary the frequency of the forced oscillator and figure out how the energy transfer is happening, how the amplitude is rising. But then that we will leave late for later, and not for all of you. Those who are enthusiastic enough, they can look into this situation. Okay. So as far as from my side, this is over. Any doubts here? Those who are sitting here? Target outcome is this. Yeah. Your input equation is this. Target output is this. Okay. You will have to select gamma, omega 0 values judiciously. So for that, I have given you that these are the relationships. So you can manufacture some values and test for it. You can also check the case, just 1 minute. You can also check the case where gamma is 0 or B is 0. So if B is 0, your solution must reduce to a constant amplitude solution, which is an ideal SHM case, right? So online friends who are viewing this, for them we will create a link, video link in some time, and we will take up their doubts also. So thank you very much. What other methods they can try? Okay. Okay. So from suggestion from Rohan sir is that they should try. Let me record it for record. That so it is strongly suggested that students should use the method other than Euler method to solve this equation. Uh, so there are many methods that you have learned in mathematical physics course, and you can use any of those. Okay, make your own life interesting. So we will end the streaming. Thank you. There are 6 people online, 6 people offline. That's a great class.